Good. Good. Introduced you to the concept of forces. Well, there are two types of forces, two types of forces. Contact force and non-contact force. Contact force, most of the forces, okay? And non-contact force. Okay. There is a very important non-contact force, that's the weight. It is given by the mass of the individual times the acceleration of gravity. Okay, this equation that you see here, even though I just gave it to you, this equation comes from Newton's second law, which we still didn't introduce to you yet. So remember this equation, right? And this force as well. Every mass on the surface of a planet nearby another mass, either the surface of a planet or nearby another mass, another planet, is subjected to a force that's called the weight. And this force is going to be the mass of the mass, the value, numeric value of the mass times the acceleration of gravity at the spot where the object is located. Here on Earth, at the surface of the Earth, this G is 10 meters per second square. On the surface of Earth, right? On the surface of Earth, comma G is equal to 10 meters per second square.
Professor, is this non-contact force or?
No, this is a non-contact force. Yeah, this is a non-contact force.
Okay.
Very few, because the mass, the object, doesn't have to be in contact with the surface of the Earth. The Earth doesn't have to be touching the object for the object to be subjected to Earth, right? Like this object here, when I release it, it falls because the Earth is attracting the object, and it doesn't have to be in contact with the Earth to feel that force. My hand is a contact force. Okay, when I lose contact with this object falls. And my hand no longer apply a force to this checkbook of mine, right? Here you go. Non-contact force, very few of these forces. The most important of them is the weight, okay, which is also called the weight is also called the gravitational force. Gravitational force. So two different names for the same thing. There are other non-contact forces, but we are not going to cover them in detail. We're going to cover them in detail with Physics 7. The other force is the magnetic force that everybody should be familiar with. Another one is the electric force. You folks are familiar, right? Static, right? Due to static electricity. You should be familiar with that as well. And then there are other forces that are, here you go, I put the electric force before the magnetic force, because we studied the electric force before the magnetic force. And there is also the strong force. Not everybody knows about this force. And there is also the weak force. 5 different non-contact forces. That's all. That's all we have. They're both nuclear force. This is a nuclear force. This is a nuclear force. They are both non-contact forces. And then we have the contact forces. The first one I introduced to you was the normal. And I abbreviated by the letter N, let's not forget. And the weight, we usually abbreviated by the letter W. Okay, there's a tension, okay? We usually abbreviate that force by the letter T. Okay, good morning, right? Thank you, thank you. Tension, and what else we have? There are more, okay? That's some of them you are familiar with. Air drag, okay? Everybody can feel the air drag. If you're driving the freeway at 60 miles an hour and you stick your hand outside the window, must be a flat hand. You're going to feel pressure from the wind coming towards you, okay? This will be the air drag, the force of the wind. I'm gonna put like that, for instance, force of the wind. It doesn't have to be air drag necessarily. Let's put that fluid drag. Force of the wind is one of, for instance, is one type of drag force. Force of the wind. We have air drag, we have water drag, right? Another one that I can mention here to you is the lift. Okay, what's this lift force? Okay, this is the force that makes airplanes fly. This is a contact force as well. And I want some illustrations for you so you can see it. Let's see if we can get that from the book. If you don't get from the book, we go in the internet. Wiley plus, let's see if the book has it. Right, Wiley plus here. And the lift is kind of a counterintuitive force. It's not an obvious force. Airplanes, in order to fly, they must, be subjected to this force, to this lift force, and this lift force is applied to the wings of an airplane. The wings of an airplane has a very particular configuration, has a very particular geometry that allows to have this lift force to exist. Let's see if we have an illustration here. If you don't have an illustration, we look into the internet, or even I start drawing here for you. Let's see. Here's an illustration of the weight, okay, applied to an individual. The ball player to the left. Let's see here. Oh yeah, here you go. Here's the contact force of one player in another one. Okay, this force that you see right in here is the force that this guy with the red helmet is applying to the guy in the yellow helmet. Okay, not only you have this force being applied to this guy here in the yellow helmet, which is to the left, but the guy in the yellow helmet is also applying a force to this other player in the red helmet. That's a contact force. Here's another contact force that I mentioned to you, and this force is the tension in this string here. There are other forces there as well. Okay, but that's the only one that was illustrated. And the arrow label represents the force that acts on A, the football player on the left. See, the football player on the left, the water skier, and the cliff diver. And those are the only the three forces that we have, right? But there are more, like I said, right? Oh, here you go. Here's another contact force, right? If you want your car move, if you want to make your car move, right? You can apply a force to the back of the car. And let me write that down, another one here for you. Here's the frictional force, force of friction. And that's the type of force that the ancients were struggling with, were struggling to understand. The ancient philosophers, force of friction. Okay, I want to give you give you an illustration of the lift force. Let's say, here you go. Oh, right here, I like this figure. See, from NASA. Lift is a mechanical aerodynamic force produced by the motion of the airplanes through the air. And here is an illustration. Wikipedia again. Huh? Here is an illustration of an airfoil. That's how the wings are shaped. That's the geometrical configuration of a wing, of an airplane. If you shape an object just like this one that you see right here, and you put it to move, okay, there's something missing here, right? He had to put a velocity vector here to the left. What's going to happen if you have this object shaped just like that? Oh, here you go. Move direction of motion. You put the direction of motion right in here. It's not in the horizontal. It's a little bit slanted. Okay, it's a little bit slanted. But this angle of the direction of motion, I wish they had made this figure in a different way. Okay, the horizontal is in this direction. Okay, folks, that's the horizontal. Note, see that this direction of motion is perpendicular to the left. Okay, and how does the lift comes about? How does the lift comes about? Well, it has all to do with the shape of this lower surface and the shape of the upper surface. When this airfoil or wing moves through the air, what happens? The air below the wing exerts a larger force on the lower surface than the upper surface. Okay, you're going to have a downward force of the air on the upper surface of the wing and an upward force on the lower surface of the wing. However, this lower force sometimes can be larger or smaller than this other force here. And that's what ends up producing lift or the lack of it. It's a very smart realization by us when we realized that we could lift an object just by shaping it in this way. We came to the point where we were able to emulate flight, not simulate, but emulate flight, right? The same wing, the same lift. Let me stop sharing and I'm going to show you, the same type of force, and then remind me to go back to sharing the screen, okay? I want you to take a look at my hand, okay? Remember, when you stick your hand out of your car that's moving at 60 miles per hour, you're going to feel this drag force, right? This pressure pushing your hand behind to the left. If you make your hand in this configuration here, now the drag is going to be very small because there is a very small surface area of your hand subjected to the wind. Okay, and you're not going to feel much of a force there because this area here, this cross-sectional area, is much smaller than this cross-sectional area. So the air drag force depends on the cross-sectional area of the object. Okay, Now, there is one more thing. We're talking just about the air drag, right? I start talking about the air drag, but now the next step is the lift. It is possible for you to feel the force of lift if you are inside your car. I used to do that when I would drive out there, okay? Someone was driving the car. I would stick my hand out just to do some experiments. And then if you shape your hand in the shape of an airfoil, put a little bit of a concavity on the upper surface, you will feel that your hand is going to get some sort of lift, okay? You can try different angles of attack. We call it angle of attack, different attitudes of your hand. And if you experiment, and then if you do something like that while you are driving the freeway, be careful not lose your hand if another car is coming by, right? Maybe if you're going to stick your hand, just stick just a little bit. You're going to feel sort of that your hand is going to become slightly lighter, just because as the air moves by your hand, the air pressure below becomes larger than the air pressure above. This is a way to experiment, to experience lift. It's not an obvious force. Okay, so here you go, the drag force right in here, see that? And there is another force that I didn't tell you yet, is the thrust. I'm gonna document there yet. Do you see how many forces are there out there? How many contact forces are there out there? Force of friction, okay, which is kind of related to drag and thrust. Hopefully I cover all of them. Okay.
Can you share your screen again?
Oh yeah.
Thank you.
Oh, here you go. Thrust. The engine of your car produces thrust. The engine of an airplane produces thrust. The engine of a rocket produces thrust. Okay, the propulsion, the engine of a missile produces thrust. And like I said, where the lift is a very difficult force to visualize, okay, this lift force. But if you do that little experiment in your car, and again, be careful not to lose your hand when you do that, right? Lift, here you go. Lift is a force that occurs whenever an airfoil shaped object moves through, not just through the air, but through a fluid as well. Okay, we can have lift underwater as well, but you have to move in the horizontal direction. Okay, when something like that happens, the fluid below, and let's put here airfoil wing, right? The fluid on the force, the fluid on the surface, on the lower surface of the wing, right? Of the wing, experience a larger pressure or force. It's not the same thing, but they are related, okay? Or force compared to the force on the upper surface of the airfoil or wing. This produces a hovering effect, right? Hovering effect. But don't forget, oh, and by the way, it's not just moving, right? There's an even better way of, when something like that happens, the fluid moves, not that the object moves through a fluid, but whenever, shaped, let's see, lift is a force that occurs whenever an airfoil shaped object moves through a fluid. I'm talking about relative motion, okay? I'm talking about relative motion of a fluid. You do not have to move with respect to the ground. You can just have a very strong wind flying towards you, coming towards you, And if you have an airfoil, the airfoil will be able to hover over the surface. Okay? You don't even have to move with respect to the ground. You have to move with respect to the fluid, and the fluid being either air or water. Okay? So it's a kind of a funny force. It's not easy to visualize that because of the unique shape of airfoils. And right in here, here's the shape of an airfoil. That's how an airfoil looks like. It's the shape of a water droplet. It's kind of the shape of a water droplet. Okay, lift. So Wikipedia has an article on lift. Is the sum of all forces? I guess that is the sum of all forces. This actually is not well left. It's not well written. It's not the sum of all forces. You have just this force that is the lift. Okay. Yeah, I don't like the way that he wrote that. It's not the sum of all the forces. There is a specific force called the lift. The sum of all the forces. And flow direction, okay? So the direction of the flow. So you can see in this case the airfoil. Let me another Wikipedia. Oh, where's that? Oh, here you go. That's the one. Another airfoil. What this is the one. Okay, here you go. Here's my tear-shaped device, and notice that the airfoil doesn't have to be moving at all. All I have to have is having a fluid flowing towards the airfoil. So if you are standing in a swimming pool and there is a water current coming towards you, if you have an airfoil shaped object, that airfoil will be subject to a lift. There will be other forces there too. There will be the drag as well. Okay? There will be a drag. And then we have those two forces, drag and lift, the aerodynamic force. What makes the object hover is the lift. Oftentimes we want to minimize drag. Oftentimes we want to minimize drag to increase velocity. That's a quick introduction about the lift. Okay, lift is the force that occurs that an object experiences, right? That an object experiences, that not an object, that an airfoil or wing experiences whenever there is a relative motion, whenever it moves with respect a fluid. That's better. That's a better way of whenever it moves with respect to a fluid. So it's a matter of relative motion, right? It's a question of relative motion. Better this way, right? A fluid. The fluid can be either air or water, right? The fluid can be either air, either a gas or a liquid. When something like that happens, the fluid on the lower surface of the wing exerts, oh man, not experience, exerts, okay, a larger pressure compared to the force that of the to the force on the upper surface of the wing. This produces a hovering effect. Okay, I want you, if you have the chance. I used to live in in El Segundo, nearby the airport. Okay? And every now and then I would walk there in the beach, and there in El Segundo, I don't know if you still have it there. They have like some sand dunes. Okay, they have a little hill in which people with gliders, they keep on practicing how to fly with their own glider there. I do not know if you've ever been there. It's a really neat place. You know, they even have a wind sock in there to know the direction of the wind. Okay, the wind in that region of El Segundo, most of the year, it blows towards the land. So the wind comes from the western direction. And those guys with a glider, they can, when the wind is very strong, they can hover above the ground, and they just stay there hovering, maneuvering a little bit to keep on. It's a really beautiful sight. If you've ever seen that. Birds does that too. Birds, they just don't fly in a straight direction. They also know how to hover above the surface when the wind is very strong. Okay, I do not know if you have ever seen that. And they keep on flapping their wings, and they usually have a very high altitude. And high altitude, that means the body of the animal, right, makes a steep angle with the horizontal while they flap, and at the same time they flap their wings and they stay hovering on the air. Okay, and watch that. If you have the opportunity to go to the beach, for it, we see that most of the time in the beach when there is a very strong breeze. Okay? Not just the beach, but also in any places that has a very strong wind. But most of the time, it's in the beach. It's in the beach because of the wind that comes from the sea. Okay. So you have those. If you can, if you may, try to walk by there in El Segundo and look for this place where they have those delta wings that the guys practice there every now and then. It's a really nice sight. Okay, and that's a example of the lift force. In the case of the thrust, thrust. The best example for thrust is that of a missile. Thrust example. Propulsion by the exiting gases of a missile or rocket. Okay? So if you propel the gases of a fuel at a high enough speed, just like in the case of jet engines, right? Like it's not just the case of rockets, but also in the existing gases of missile or rocket, of a missile, rocket, or jet engines too. Jet engines. If propel the gas of a fuel at high speed, at a speed high enough, right? At a speed high enough, you produce a force that propels the object. And it doesn't have to be gases, it can be liquids too. Okay, let's take a look at an example. And the propeller of an airplane, for instance, is not exactly a jet engine, but works in a similar way. The propeller of an airplane is just a very big fan that exerts a force on the air. once the propeller propels the air backwards, the air propels the propeller forward. Okay, so in principle, the fan that you have at home can be used as a propeller. If you put your fan on a surface that has very little friction, your fan will be able to move. Okay, so those are the list. Yeah, thrust. Let's see if we can have an illustration of thrust here. That's the lift. Let's see, thrust. Thrust is a reaction force. We call it a reaction force, and you're going to see why we call it that. Here you go. Here's the jet engine of an aircraft, propelling it forwards. Okay. Fixed wing aircraft propulsion system generates forward thrust when air is pushed in the direction opposite to flight. Okay. Fixed wing generates forward thrust when air is pushed in the direction opposite to flight. This can be done by different means, such as the spinning blades of a propeller, like I mentioned to you. Here you go. Here's the propeller. The fan-like device that's installed in propeller airplanes. The propelling jet of a jet engine. Okay. So the jet that comes out of the nozzle of this aircraft is the result of the combustion of the jet fuel by ejecting hot gases from a rocket engine as well. Three different. Here you go, rocket engine. See the hot gases? This hot gases is producing a thrust perpendicular to the exit nozzle. Reverse thrust can be generated to aid braking after landing by reversing the pitch of variable pitch propeller blades. Yeah, you can do that. Or you can also, some airplanes used to have some jet airplanes used to rotate the engine, okay? Used to rotate the engine to reverse. Here you go, here's the engine. But then they abolished this thing because there was an accident, thrust reversal, also called reverse thrust. You can rotate the engine in the opposite direction to brake the airplane. But then, there was a bad accident with an airplane in which, for some reason, the jet engine revert direction during flight, and then they abolish this type of reverse thrust, thrust reverser. Okay. Okay, so now we should have a very good idea of the types of force that we have in there. And don't forget, force is a vector. Okay, and we have in physics what we call to solve problems in physics. Solve problems in physics involving forces. We must always keep track of every force subjected by an object. Okay, since forces are vectorial in nature, they can be represented by an arrow. Just okay. The resulting diagram showing the vector forces applied to an object, it's called a force diagram. No, not force diagram, free body diagram. Free body or force, okay? Or force diagram. You have and you must become familiar with this type of diagram. Okay, you must become familiar with this type of diagram. And the very first free body diagram is this one that you saw, right? That I showed to you. Here you go. Here's the force, the normal force that the surface is applying to this object. Okay, more accurately, that would be the right drawing that you should be looking at. At this point here, that is a contact between the object and the surface. Okay, I just raised the object so you understand that this force is applied to this block. Okay, and if the object is touching the wall, there will be this other normal force applied to it. Don't forget the velocity of the object is 0. And in order for the velocity of the object to be 0, okay, this force alone, it should not be correct to draw a diagram like that, because this implies that this object would have a net force to the left upwards. Okay, but since the object is at rest, there must be other forces here that I'm not documenting. This free body diagram is an incomplete free body diagram. Okay, that's what I mean. Okay, a more complete free body diagram is one that shows another force applied to the object to the right. This force N2 exists because I'm applying my hand at this object to the right. And this force N1 exists because there is another force pointing downward, which, by the way, is the weight. Okay? The weight is always there. The weight is always there, will always be there in our problems. Because the object at rest, the net force is 0. And that's where we go back to that vectorial equation that I introduced to you before. And I'm going to here write it. You go. For an object at rest, over its surface, we have the following vectorial equation for the forces acting. Not just for the forces and the net force acting on the object. Like that. Net force is equal to normal plus weight. Okay, and this equation works specifically for this example here. Let's see here, the snipping tool. You go. I will copy this drawing. Don't forget the free body diagram, and I will paste to my note. I will paste this figure to my notes. Here you go. We can have another free body diagram, right? I gave you another illustration of a free body diagram. This one right in here. But there is a missing force here that I told you, right? What force is missing here is the weight that's missing that free body diagram. Okay. Another example of free body diagram is this one right in here. Okay. I will copy. Now, don't forget, now the drawing is complete. We have all the forces that we have that is being applied to the object. Okay. For this diagram here, for this other free body diagram, we have the following vectorial equation. Okay, we have not just n plus w, but that's going to be, I put n, right? Yeah, I put n, that's good. So we leave n. Here, this one's going to be n1 plus w. I'm going to put like that. Plus n2 plus, don't forget n. Don't forget this is vectorial equation. It's not a scalar equation, right? This force here cancels out with this force, and this force here cancels out with this force, okay? This force plus this force is equal to 0. This force plus this force is equal to 0. From the diagram, okay, from the diagram, this plus this is equal to 0. And this plus this is equal to 0. This plus this is equal to 0. Note, see that there's a reason why I wrote the formula in this way. Note, see that n1 plus n3 is not equal to 0. It's different of 0. It's why it's different of 0, right? Going back here, why is it n1 plus n3 is different of 0? And what happened here? Oh, I'm in the wrong page. Oh, see, good. I'll see that. Just look at the drawing. N1 is upwards, N2 is horizontal. So definitely N1 plus N3 is going to be different of 0. Similar, N1 plus N2 is going to be different of 0 as well. Okay? So also, N1 plus N2 different of 0, right? And the same would apply for the weight. The same should apply for, here you go. I'll copy those, because the weight is in the vertical direction. We would have the same situation, right? Here and here. We have similarly for the weight. Notice that, oh my goodness, I did something I shouldn't have done. Let's see. That's supposed to be N1 here. N1 right here. Good. Likewise for the weight. Likewise for the weight. Okay. They should be 0. They should be different of 0. All those relations. But, you know, those two are 0. That's why this net force here is 0. And the net force is 0. And the net force is 0 because the object is at rest. Newton's first law. Newton's first law. Or let's say the first part of Newton's first law, right? The first part, I'm going to write it down. The first part of Newton's first law. Like I said, the ancients, you know, understood that very well. What they did not understand what they did not understand was the second part of Newton's first law. Even Galileo himself didn't quite understand the second part of Newton's first law, but he almost got it. Galileo himself did not understand law, but he almost got it right. Almost. Okay. You almost became millionaire, right? You almost became famous. Just like that movie, Almost Famous. I don't know if you watched that movie. Galileo did very superb work for his time, but this one, he almost got it right. Almost. It was Newton who got it completely right. So what's the second part of Newton's first law? Now I can introduce that to you, the second part of Newton's first law. And it's not easy to see that if you do not have the technology that we have today. I remember when I was a young man, we didn't have those arcade games like the table hockey, the hockey table, right? That we have in the arcades. I didn't have that at my time. Things like that was very difficult to see. And because we didn't have those, here you go, hockey tables, right? Let's take a look. Hockey tables. Everybody know about that? Hockey table? Hockey table game. Someone gave me one of those as a gift some time ago. Okay, so what is this hockey table game? Right, it's just a table, a regular table, a flat table with a bunch of holes here. You must have played that game, right? See the holes here in the table? Oops. And then you pump air into this table and you have here you go, better. You have air coming out of this table and those pucks, they float. They float, oh, this puck, sorry, this puck here, float over the table. They hover, right? It hovers. Since it's hovering, there is no friction whatsoever between the surface of the disc and the surface of the table. And this device is a very nice example of the second part of Newton's first law at play. Okay? Think about that. Back in 1981, it was the first time that I saw something like that in my whole life. At that time, I was 17 years old. I was going from 17 to 18 years old. I was just fresh into university. I was a freshman in the university in Brazil. And they showed a device similar to this one, an air track. We don't call it air table. We don't call it a hockey table, right? We call it an air track. And today, nowadays for you, you have seen that so many times, right? It's nothing surprising, but for me at that time it was very surprising. I had this little device floating in this air mattress, right? And the moment I propel it, it shouldn't stop, just kept on moving back and forth, back and forth. That's because there is no friction between the cart and the surface of either the table or the air track. When I saw that for the first time, I had the feeling that there was this invisible finger driving the car along the track. And I'm talking about the air track. Air track. Air track, you go. Must be one like that. Is that this one here? Let's see. No, it's not this one. Strange. They call about inflatable tracks. That's not what I want. Okay, this one here, air track. Wikipedia again, right? Wikipedia saved the day. The way air tracks works, function, is very similar to the way air tables work, function as well. This classroom looks like the classroom at LA Harbor. The table is very similar. We just don't have those drawers here on the side. But here you go. Here's the track. This track also has a bunch of air, a bunch of holes here. Let's see if we can see the holes now. We cannot see the holes. Okay. We have a pump, air pump here, connected to this nozzle in the air track. We turn on the pump. Water is rushed inside this air track. Don't forget this guy is hollow, right? And high pressurized air comes out from the holes that are in the surface, creating a hovering effect, right? Making the cart here, this cart, hover, is being lifted. The moment you propel this cart doesn't keep on moving almost forever, you know, back and forth, back and forth. And that's where we come with the idea. Don't forget the track must be leveled. And that's where a very good example of Newton's first law, the second part of Newton's first law of motion. Oh, now I gotta get out of here. How do I get out of here? Here you go. Nope. Here you go. Now, more. Second part of Newton's first law. And I'm going to just copy and paste what I had before. Don't forget, folks, this the second part was not as obvious to the ancients because they didn't have the technology. Newton could picture it. Galileo almost got there. He didn't quite got it right, but he almost got there. And today we just go into the arcade and see second part of Newton's first law at work. Okay, so here you go. Remember, if an object that for first part is if an object is at rest, then the net force applied to this object is 0. Okay. Second Newton's law is slightly different. Second Newton's law is slightly different. If an object is moving with constant velocity, and constant velocity means what? Constant velocity means constant speed in a straight line, motion with constant speed. Motion with a constant speed in a straight line, okay? Then the net force applied to this object is 0. Okay? Okay. The converse is not necessarily true because the object can be at rest. Okay? It's not necessarily true. In other words, if the net force applied to the object is 0, it may not necessarily be moving with constant velocity. It may not be necessarily moving with constant velocity. It may be doing something else, and this something else is, or it may be at rest instead, right? Okay. It may be at rest instead. Okay. And so now we can, I'm gonna copy and paste the first part of Newton's second law right here. They're side by side. If an object is at rest, then the net force applied to the object is 0. The converse is not necessarily true. In other words, if the net force applied to the object is 0, it may be moving with constant velocity. Okay, it may be moving with constant velocity. So I'm gonna change it here. In other words, this is the net. In other words, see how we can improve the text, making it shorter and shorter. In other words, if the net force applied to it may be at rest. Okay? It may. Can you remember that? Can you memorize that? Constant velocity at zero, net force is equal to zero. Velocity constant, net force is equal to zero. Okay? So combining these two parts into a single statement, we have the following. We have Newton's first law of motion, comma. If the net force applied to an object is zero, the object will be either at rest or moving with constant velocity. And the converse in this case is true. The converse in this case is also true. In other words, if an object is at rest or moving with constant velocity, see how we combine everything into a single statement, or moving with constant velocity, then the net force applied to this object is zero. And I'm going to emphasize here, net force. Okay, and I'm going to put in a different line. You have to memorize that for the rest of your lives. Okay, this statement is, let's see, the converse in this case is also true. So it goes both ways. Okay. Here doesn't go both ways because I'm referring just to constant velocity. Here doesn't go both ways because I'm referring just to velocity is equal to zero. But here goes both ways. That goes at both ways because the object is either at rest or moving with constant velocity. Yeah, both is also true. 9:51. Any questions? Am I missing any messages from you? Okay. Okay, so let me take attendance, and when we come back, we go for our lab, so-called lab between quotes activity, right? And let's see, participants. Let's start with Sky. Are you there, Sky?
I'm here.
Thank you. Tessa, are you there?
I'm here.
Thank you. Destiny.
I'm here.
Thank you. Gael Garcia. What happened to Gael? He didn't come last time, huh? Okay. Ridwan is here, right? Thank you. Ashley Izumo. Ashley's not here either. Let's see, next one. Norberto. Thank you, Norberto. Annabelle. Hello, Annabelle. I can see you are there, but you're not here.
Hi, I'm here.
Okay, thank you. Vanessa.
Here.
Okay, that's Moon. Anna's Moon is no longer here. Let's see. Take it out and put it here. Next, Catherine Pacheco.
I'm here.
Thank you, Catherine. Camden. Hello, Camden. Brandon was the first one to arrive today. Okay, I'm gonna put a little star here, Captain. Here you go, Victoria Preciado.
Here.
Thank you, Lexis.
Here.
Thank you. And Donovan is not here, right? Let me take him out. Last but not least, Marco Sanchez. Thank you. Let's see how many students we have. Should have 12, but one didn't answer, so we have 11. Good. 9:53 right now. Any questions before we proceed? For our break, let me go. I will save that and break from 9:55 a.m. to 10 a.m. So I see you in 10 minutes. In 15
Professor,
Yes.
I'm here too.
Okay, thank you. And then you go. Now we have it. 12 students. And I see you in 15 minutes. Okay, I'm back here. Okay, and now, okay, I moved a little bit forward with Newton's law. We didn't finish chapter 4 yet, so we are, let's say, one chapter behind, right? Almost one chapter behind, but I moved forward enough. And I want you to remember Newton's first law of motion. Let's see, second part. Okay, we have, you go. I'm going to bold face it. Huh? Oh, I'm gonna emphasize the or here as well. And don't forget, that was the second part that the ancients didn't quite understand it. Okay, they thought that for the object to stay moving in motion, to remain in motion, they thought that a force was necessary, a net force different of zero was necessary for the object to continue in motion. And that was due to the fact that they didn't quite understand the force of friction either, okay? They didn't quite understand the force of friction either. But Newton finally managed to fix that with the help of Galileo, of course. With the help of Galileo. And what we have right now is going to be our lab number 2. Lab 2. All those labs we do there at the Lake Harbor with the equipment that we have. Unfortunately, we cannot do that. The
Hello?
actual experiments.
Professor, are we going to use the Excel again?
Yes, we're going to use the Excel spreadsheet again. I'm going to upload the Excel spreadsheet to your group. Oh, and by the way, right, let me just remind you, lab report, right? For lab 1 is due, right? Is due. Please upload your Excel spreadsheet and Word documents into your folder. Just one of each document per group, right? So the format for both documents, is P06. How did I do that? Let's take a look at the syllabus, right? The syllabus is spelled out exactly how you are supposed to entitle the document. So let's stick to the syllabus. P06, according to the syllabus, is going to be L01, right? L for lab, 01, group XX. One document is going to be a XLS document, right? The other one with the same, exactly the same title is going to be a docx. Docx or doc. I always thought that those extensions were only 3 letters. Okay, please keep that exactly this way. Don't put any one in there. Don't put any copy there. Don't spell out lab. I want everything with every one of those documents exactly this way. And don't forget to put your group number, right? Group 01, group 02, group 03, and so on. I keep, thousands of those spreadsheets in my hard drive here at home, here in my computer. And let's go for our lab 2 spreadsheet. Go. It's amazing. I started doing something like that back in 2015. Okay, back in 2015, I started to do the lab in this format. I started using my Google folders there for my students back in 2014, and it has been working well. Has been working very well. I never had to change it. Drive. Drive. Let's see, this is what I want. Drive. Here you go. Got it. Fall folder 2023, physics 6. Okay, group 1. Oh no, wait a minute, I gotta change here. Something here I have to change. Changing. Oh. Oops. Oops. Group 1, you have your spreadsheet there. Group 2, you have your spreadsheet there. Group 3, just uploaded your spreadsheet. Group 4, don't forget it's lab 02, okay? The one that we are doing right now. And group 6. Okay. So you can go ahead and download it. I'm going to use here this one as my sample. Let me know whenever you come to a point where you, Professor, can you remind us how the Word document is supposed to look again when turning it in? Or is there an example where, let me see if I have a sample here. I remember posting a sample last time I taught this course. My drive. Oh, well, looks like here. Let's see. See my hard drive. Okay. Let's see, corrected. Hard copy. Okay. So here we go. Let's see. No, this is not a good one. Okay, I'm gonna post this one here. I'm gonna post this one there, but I don't want student one. Student one. Student two. Student three. Two. Sample. Have been able to download the spreadsheet? I am saving it and see if I can get that. Okay. Now, what am I going to do here? Okay, I'm gonna put, I'm just gonna copy into everybody's folder, okay? Every group's folder, okay? You read one. Group three. Group three, you have a sample for the Word document. Group four, group 1, 2, 3, 4. Oops. 1, 2, 3, 4, and 5. You all have a sample of the Word document. It's docx. So look for this document right here in your group folder. Group 1. Let's see. Wait a minute. Oh gosh, no, I put in the wrong. Sorry. I put in the wrong place. Yeah. Okay, now I'm gonna put it in the right place. Okay, group 1, group 2, group 3, group 4, group 5. Okay, now you have a sample. You have the sample document there. Group 1, good. I'm gonna show you everybody's. Okay, so here you go, group 1. I see your spreadsheet, but I don't see your Word document. Okay, Here's the sample. Group 2, I see your spreadsheet, but I don't see your Word or PDF document. Doesn't have to be a Word document, can be a PDF document. Group 3. Okay, group 3 has it.
Mhm.
Okay. Here's a sample. And group 4. I see here. Okay. Group 4 has the hard copy. And the last one is group 5. Yeah, and group 5 has it. So it's just group 1 and 2, right? Just group 1 and 2, which does not have it. Yeah. Make sure you upload it as soon as possible. And that's our,
Professor,
yeah.
so from lab 2 spreadsheet, do we need to convert this scientific value to number?
Yeah, but I'll get there. You gotta do exactly the same thing you did before, right? But I'm going to explain the experiment first, and then you can start doing. We are right here, okay? We are right here. Laws of motion, right? Okay, we didn't do uniform circular motion, unfortunately, so we have to adjust the schedule. Have to adjust the schedule. Uniform circular. Hopefully, we will be able to do chapter 5 and 6 next time, right? Okay, report 1 do. Now let's take a look at my. Already have the spreadsheet here, right? Here's the attendance. Here's the spreadsheet, and okay, don't forget put your group number here. Student number 1, 2, 3, 4. The date. Most likely there is no student 4, right? So just leave it in blank. Don't change anything in this configuration. In this spreadsheet, don't change the order of the tables. Here's the G, already have the meters per second square, and each of those parameters means something, and I'm going to brief you on how the experiment is done so you understand what you're doing, okay? Actual notes. Okay, so uniformly accelerated motion, okay? Remember that I told you about the air table, air hockey table, right? Remember I told you about the air hockey table and the air track as well, and the air track as well, right? This experiment is done with an air track. You already saw a picture of an air track. And it is illustrated right here in my slides. Okay, here's my air track, and you saw that before, an actual picture of the air track. It's an aluminum track. Here's the air table. Oh, here you go. Here's an aluminum track. That's very similar to what we have there at LA Harbor. Okay. And then we have our cart. Okay. The drawing that I made here is exactly that. And I'm going to, I'm going to eliminate some of the stuff here. So, we start with a table, right? Here you go. We start with a table. After the table, we put an air track, the track here. I don't want this cart yet. I'm playing the movie here for you. Here you go. This track has 2 legs. Actually, it's 3 legs. Okay. One of them is adjustable. This other one is actually two foot. This one is 1 foot. This is 2 foot. Okay, and you have all those little air holes. Have all those holes in there. All holes and drilled into this hollow air track. The cross section is a triangular section. The cross section of this track is a triangular one. Let's take a look here. Here you go. Triangular cross section. Okay. This drawing has the picture has too much information in there. So here you go. Air track. The distance between those 2 legs is what I call in the spreadsheet B. Okay? We're going to need the distance between those 2 legs. And we go B right in here. You have to put the units, the proper units. Let's take a look at it's roughly 1 meter. Okay? Roughly 1 meter. So in this experiment, we use the following. Okay, here we go. In this experiment, we use the following equipment. 1 air track. 2 ruler. And at this point in time, you know that the resolution of the ruler is what? You know, resolution 0.001 meter. And now you know up to which decimal place you can display your number there. Air track, ruler. Okay, you're going to measure B with the ruler. At least as of now, you're going to measure B. Right? I'm going to close this guy here. I'm walking you through the experiment, okay? Exactly how we do that in the classroom. The next thing that you're going to do, you're going to connect a hose. Oops. A hose to this end of the track. You can see the holes right now. See that? And by the way, the hose connects to a nozzle. I didn't illustrate the nozzle in my drawing, but I can do that. Let me illustrate a nozzle here. Here you go. I'm going to illustrate the nozzle like a short hose. Okay, here you go. Here you go. That's the nozzle. Okay. Nozzle. Nozzle. Okay. And the hose catches with the nozzle. What else we have? We have a pump, an air pump. It's not exactly a vacuum cleaner. It's something a little bit, something the opposite of a vacuum cleaner. I'm going to change my drawing. Let me change my drawing here. There you go. I'm gonna make my holes a little bit larger, okay? Otherwise, it's not very realistic. You go like that. Oh, this computer is behaving. Holes. Should I write that down? Holes. You want to do like that? Even better. Table, right? Table. Here you go. Next one is going to be air track, like that. Air track. Every time I introduce a new device, I put a new element to my drawing. I put a name there. And here is going to be the nozzle. Nozzle. I don't need to introduce the nozzle again because I already introduced it. The distance between the two legs is B, approximately 1 meter. And then holes. Holes. The next one, pump. Here you go, pump. Here you go, pump. I don't want to keep everything in there or all the description there, otherwise it's gonna become too busy, right? Here you go, table, air track, nozzle, distance between legs, B, hose, and pump. Next in line, I don't need that anymore. I don't need that anymore. Okay. Next is going to be my cart. And now I'm going to, erase this guy here, otherwise it's going to become too busy. If needed, I come back to that. That's going to be my cart. We also call it a glider. Okay. Cart. The length of the cart is L. Glider / cart. Length of the cart is L. And let's take a look. And let's see, I want this guy to cover the holes, right? Everything okay there? Well, let's see how I'm going to do that. Fill. Okay, good. Like that. And let's see, am I missing anything in my descriptions there? All right, let's go back here. Ruler. B. Measure B. You go. Air track. Hose. Air pump. Same type of pump that pumps air into the tire of your car. Okay? That's what I mean by the air pump. Glider / cart. Length L. And it's also measured with the ruler. Let's take a look here. Here you go. We are right here at this spot. This L is around 12 centimeters. Okay. So you should know how many significant digits to display here. Going back here. Oh, I don't need that anymore. Can erase this guy, right? Okay. So what are we going to do with this thing? We're going to put a shim, okay, at the other end of the track. That's the shim here. And let's see here. Let's see if I can get it right. Group. Okay. What do I mean by the shim? Well, now, in order to incline the track, I have to have a shim there. Here's the leg of my like that. It's no longer a glue, right? Now it's a shim. Shim. Just to raise the side of the track. Let's see here. Yeah, I didn't document that, but I'm going to document that right now. This height here. I don't need the L anymore, right? This shim has a height of H, which is documented in your spreadsheet. Right in here. Meters. Okay.
Can I see the default value from the beginning?
What
Please.
default value?
The measurement value, like that be approximated 1 meter, like that.
Oh,
that.
it's in your spreadsheet. Don't you have it there?
Oh, so it's written in scientific form.
Yeah,
From
it's written in your spreadsheet. Okay, so let's see if I group, let's see. No, it's not what I want. The nozzle, hey, okay. But this H is so small, right? There you go. So difficult to see. Okay, and well, by doing something like that, by inclining the track, this cart will move with constant acceleration. Okay. So let's one by one. Table, air track, nozzle, distance between the legs, hose, pump, glider or cart with length L, shim of height H. What's the role of the shim there? The role of the shim is to accelerate the cart, right? So going back here, glider, cart, shim, to raise one end of the track and to produce an acceleration for the cart. The height of the shim is H. And this one, by the way, is measured not with the ruler. This one is measured by the micrometer, okay? My micrometer that has a resolution of 0.01 millimeters, which, by the way, is 1, 2, 3, right? Meters, 1, 2, 3, 4. 1, 2, 3, 4. Okay. 0.01 millimeters equal to that. That's the role of the shim, to raise one end of the track and impair an acceleration to the cart, and impair an acceleration to the cart. The shim has a height H, it's measured by the micrometer. Consequently, let's go there. So this table, right? We have everything in this table now. First was the B, then the length of the cart, then the H. I'm gonna tell you why do we need all those parameters. And we have the G as well. You don't have to worry about the significant figures of the G. Everything in red, you don't have to worry about significant figures of the G. 1047, here you go, that's the height of the shim is almost 13 millimeters, 1.3 centimeters. Here's 1 meter. No, he's not 1 meter. He's around 12 centimeters. He's around 1 meter. Okay, and what else do we need? Okay, I'm gonna bring my cart to the top. To the top of the track. That's exactly how we do in the experiment. Okay? And we are going to release this cart. Let's see here. Let's see what else I have here. Oh, yeah, okay. I don't need the shim anymore. I don't need that. I don't need that, right? Next. I don't need that either. I put the shim a little bit higher, right? Yeah, no, we have the same height. Okay. It's just the legs that I put higher in the previous drawing. Okay, take it out. I'm going to raise a little bit more. Right in here. A little bit more. Okay. Okay, this position here of the cart, of the front bumper of the cart, is going to be what I call the position X. Okay, and here you go. Here's my coordinate axis, X axis. And I'm going to call this position, this coordinate axis is actually a ruler that's imprinted in this cart, in this track. Let's see if we can see the ruler here. A little bit. I'll have to download this drawing. See, we can barely see it. Let's see. Many of those tracks, they do have a ruler there. Do you see the ruler here? It's a tape. See that? It's almost 2 meters long, maybe 1 meter and 80. Okay. And that was going to serve us as our x-axis. Here you go, x-axis. My 0 is here. I'm going to put that in red color. And sticker. Okay. Let's put that in red as well, so you know it belongs to the axis. And the origin of my axis is going to be right in here. And the position of the front bumper of the cart, I call it big X to distinguish from the small x. Okay, that's the position. And I do have the X right in here in the other table, okay? I do have the X right in there. And I'm going to change. I'm going to get there. You're going to understand what's happening. Okay. Oh, okay. What's next? Okay. I'm going to keep this axis there for now. In the next step, we are going to use a device called the photogate. Okay. And this photogate is going to be placed at a position Y, big Y. I'm going to explain what this photogate is all about. Not everybody knows. Yeah. Well, for some reason, man, this computer started to behave so strangely after I did some maintenance on it. Now maybe this one. Let's see. Yeah, I guess I got it now. Good. Let's shorten it. Okay, right in here. Okay. Yeah, I'll get rid of this axis. Good. Now it's sort of the way I want. Photogate right in here. I'm gonna give you a little drawing of how this photogate look like. What you see right in here is the side view of the photogate. What you see right in here is the front view of the photogate. This photogate is a timing device. It's a device that can count time, just like your timer. this device, this photo gate, is a timer, right? And how it's built is it has this jaw right in here, in this exact shape. Here we have a LED, just like the LED that you have in your remote. Okay, in your remote, TV remote, you have an LED that you cannot see the light. It's an infrared LED. And this infrared LED emits a beam of light that is collected by a photodetector. A photodetector is just like an artificial eye. Okay, when the light is on, this photodetector says that, hey, the light is on. When this light is off, this photodetector says, hey, this light is off. Okay, that's how the photo gate works. And I'm going to tell you more about this photo gate. Here we go. Shim, right? What else we have? Photo gate. Position it. Photo gate at position Y. This is a timer that uses a beam of light to time the amount of time that the light beam is interrupted. Interrupted. Okay. And you do have a, let's see, let's take a look at the internet again. We do have here you go. See the photo gate right in here? We have another photo gate here, right? It doesn't have this photo gate they put in a little rod, right? They attach it to a little rod, but the actual device is this thing right here, and it's attached to an electronic device that displays the amount of time. Once the beam here, the light beam, the invisible light beam in the infrared region is interrupted. So if this car flies by this beam, we see this flag here, this flag is going to interrupt this beam, and the amount of time that the beam is interrupted is displayed by this device here. Okay, so okay, this timer has a resolution of 0.1 milliseconds, which is equal to 0.1231 seconds. Okay, 10,000ths of a second. That's the resolution of the photo gate. Think about that. Our watches, right? Our timers in the cell phone has a resolution of 100th of a second, 100th of a second. This device here is, twice as 100 times, has a resolution 100 times better. The resolution of this photo gate is 100 times better than our timers, than our own timers in the calculator. Okay. And now let's see, position Y, photo gate at position Y. So the photo gate is a timer. The photo gate is a timer. It's a timer. Already have that. That uses is a timer with a resolution. Let's put that. I'm gonna rebuild this phrase here. Is a timer with a resolution of, okay, this timer uses a beam of infrared light, IR for infrared, to time the amount of, to determine to determine the amount of time, that the light beam is interrupted. With the beam of red light and a detector and a photo detector. Determine the amount of time. When this beam of light is interrupted and the photo detector does not detect any light, okay, the timer is turned on. The timer is turned on. Okay, and it has a very good resolution, right? It's better than resolution than what people use in Formula One cars. If you watch Formula One races, right? The timer that they have in there is 1,000th of a second. This one is 10,000th of a second. The resolution of our photo gate is 10 times better than the resolution of the timers used to time the Formula One races. The only difference that we are talking about the small cars here. Larger cars, has that timer with that resolution. It's 11 o'clock right now. Any questions so far? Okay, I want to take a little break again, right? Break, 11 o'clock to 11:15 a.m. Let's do that. Professor, can you remind us how the Word document? Okay, so I already posted the Word document. Okay, there we go. And I see you in, let's go get one more minute here, right? Since it's 11:01. I see you at 11:16 a.m. See you soon. Okay, I'm back here. Okay, so are we done here? It looks like we're done. We have everything. But I have to document those. Let's see, I did document that in my notes, right? So we're using an air track, we're using a ruler, a hose, an air pump, a glider, and a cart, a shim, and let's see, shim, and oh yeah, let me put something else here. And let's put the micrometer, right? I'm using the micrometer, right? Resolution. And we are using a photo gauge measured with the micrometer. And I put the resolution here on the other. Hey, wait a minute. Micrometer. Yeah, that's the resolution of the micrometer. Here you go. Photo gauge position Y. Okay. Photo gauge timer is with a resolution point on milliseconds. Milliseconds. When you see here, that's the resolution of the. Going back to my right in here. Okay. And then what do we do? Going back also here to my. Okay, what we have here, we have different measurements of the position of the photo gate. There's a very nice procedure to determine the position of the photo gate. We make like 5 measurements of the position of the photo gate. It's a very nice procedure to determine the position of this photo gate. And how is it done? I will, oops. I will group that. Okay, we approach the card very slowly. Okay, the way we do it, we approach the card very slowly to the photo gate and watch for the moment in which a little light LED, a little LED is not the infrared LED, but it's a red LED that turns on. Okay, when the card is about to interrupt this beam here of light of the photo gate, there is this red light in the photo gate that turns momentarily, that turns on. Okay, while the beam is interrupted, the red LED turns on in the photo gate. I'm going to document that for you. So we have the photo gate. The photo gate has the IR LED, has a photodiode sensitive to the IR LED, and it also has a second LED. It also has an indicator, let's put an indicator LED, has a red indicator LED, red indicator LED. When the beam of light between the IR, the infrared LED, and the photodiode is interrupted, remember the photodiode is just like an eye, right? The photodiode tells you whether the light is on or off. Okay, photodiode sensitive, it behaves just like the human eye, and it is used to determine if the IR light is on or off. Okay, so the photo gate has this infrared LED, has the following components, right? Has the following components. One, an infrared LED. Two, a photodiode sensitive to the infrared LED. The photodiode behaves just like the human eye. The photodiode behaves just like the human eye and is used to determine if the infrared light is on or off. And a red LED indicator. Red, so that's the new one that I didn't tell you before, right? When the beam of light between the infrared LED and the photodiode is interrupted, the red LED turns on, okay? And, okay, so we measure the position of this card just by approaching the bumper of the card to this photodiode, to this photo gate. When the light turns on, you know, we move the car just a little bit behind and look at the position of the front bumper of this car to determine the position, okay? This red LED, oh gosh, what am I doing here? This red LED is used to find the position of the photo gate using the card. That's the procedure that we do. And we get 5 measurements. We get 5 measurements of Y using this procedure. Okay? And that those 5 measurements are all about here. Okay? They're almost the same. 0.25, they shouldn't change much, okay, 0.25, right? But don't forget, those Y measurements are measured with the ruler, right? Y measurements measured with the tape which has a resolution similar to that of the ruler. Similar of the ruler, 0.1 centimeters. Let's see, 1 millimeter, which is equal to 0.001 meters. Don't forget to display all those measurements with the right resolution. Then you're going to sum all those measurements right here. You gotta display the summation with the right resolution, and then you take the average, which must be displayed with the right resolution as well. Okay? Now recall that we use the photo gate to determine how long the cart, to determine the time frame, right? And I'm going to tell you what time frame I'm going to determine here. This experiment is done in the following way. We bring the cart uphill, okay? The first position, release the cart. The cart is going to, move through the photo gate, and the amount of time that the cart takes to move through the photo gate is going to be indicated in the photo gate. Okay, this upper portion of the cart blocks this beam of light, and the timer in the photo gate is going to tell us how long the beam of light is blocked. That's how we do this experiment. So that's what those measurements are all about. Okay, so we release the cart from our first X position. We call it position 75. Okay, here you go. Here is my first X position. And then we repeated the experiment for different points where the cart is released. The higher the cart is here in the track, the faster it gets until it crosses the photo gate, right? The lower the cart is in the track, the smaller the speed that it goes through the photo gate. Okay? And I'm going to go the Y measurement. Okay. We take 5 measurements of Y using the photo gate and the cart. Okay. Next is the actual experiment, right? Next is the actual experiment. We release, we bring the cart to the highest position along the track and release it. The cart crosses the photo gate, which produce a time measurement of how long it took for the cart to cross it. Okay, so that's what it is. The actual experiment, right? So here you go. Here's the time it takes for the cart to cross the photo gate, 0.3266 seconds, right? Here is the initial position of the cart. In this case, it's 75 centimeters only. 75 centimeters only. The distance D, okay, the distance D is X minus Y, okay? Let me show you exactly. Here you go. Don't forget the cart is released from here. This distance from the front bumper of the cart until the middle of the photo gate is the distance D. So it should be magnitude of X minus Y. Okay? And what we do, we release the cart from different heights. We get different times that the cart takes to go by the photo gate. Okay? We get this distance D. The distance D is going to vary as we vary the position X, right? The position Y doesn't change. The photo gate position doesn't change. The velocity of the cart is going to be what? is going to be the length of the cart divided by the time it took to cross the photo gate. That's the velocity. Don't forget to put the units there, right? Then we take the square of the velocity. Why do we take the square of velocity? There's a reason for that. There's a reason for that. Okay? Don't forget, significant digits, significant digits, significant digits, significant digits, significant digits here. Okay. So we have the following measurements, right? We have the following measurements. L, comma, I'm gonna put everything here. L, comma, B. We have, which other one we have here? LBH, yeah. LBH, we have T, we have X, we have Y. Okay, nothing else. We have the following results. What we have D, that is magnitude of X minus Y, the distance. Okay, we have V, we have V squared. Do we have anything else as a result? Let's take a look there. Let's take a look there. Okay, here you go. Different Y's. Okay, here you go. We have different Y's. Well, I'm gonna put Y1, Y2, Y3, Y4, and Y5. That's what we have here. And what else we have here as a measurement? We have Y, the average, okay? The Y as the average. That would be the right way of displaying that. Oops. Yeah. Here you go. That's what I want. Please. What? Okay. And we have this result here, right? That is the average of those 5 Y's. Watch out for the significant digits. V and V square. Result. Okay, this is also a result. Okay. Because I give not a result. I don't know what to call that. It's not a measurement, neither a result. It's the result from a previous experiment. You can say, yeah, it's a result from a previous experiment that I didn't. But it doesn't need a significant digit, okay? And now that I have all this data, including the results, okay, we are going to use the following formula to plot our graph. We use the following formula that we saw in the lecture. Let's get that right in here. 11:32, we have time. V square equal to V naught square plus 2AD, right? 2AD. Remember of this formula? This V naught, since you are releasing the card from rest, V naught is going to be 0, right? And we have this relation that we see here. The acceleration should be the same because it's just a single inclination. But the V square and the D should be different, okay? Plot V square along the y-axis and D along the x-axis. The slope should B to A should be equal to A. Okay. Like that. Let's plot it. Here you go, V square and D. Notice that the D is on to the left of the V square. Let's see, someone is asking a question here. Hey, Professor, just plot group choose talking. Okay. Okay. Okay, good. So let's plot our graph here. Insert chart. Here you go. That's what I'm getting for this graph. Okay, there is a big blank space here. There's a big blank space here. Make sure you optimize the space in this graph, okay? And you gotta put V square here and the unit of V square. You gotta put D here and the unit of D. Make sure you increase the size of those fonts, right? And then what you have to do, here you go, add trend line, display equation chart. Okay, those guys are so small. Okay, so that's what I'm getting here. 02603. That's the slope. That's the slope, and you log the slope right here. Right here, don't forget to put the units of the slope as well. Okay, and the slope is 0.2603. 0.2603. What's the percentage difference? Look at the percentage difference here, only 26%. But how do I get the percentage difference, right? I get the percentage difference by first determining the acceleration. The acceleration is going to be half this value, according to the equation. And then we use this acceleration to calculate the experimental value of the acceleration of gravity. The experimental value of the acceleration of gravity is going to be given by this equation that you see right here. Okay, F17, right? And then you have to use the height of your shima and the distance between the legs of the track. Okay, I spelled that out all in my lab manual there. How do I get to this equation? And that's going to be my experimental G. And I compare this experimental G that I got in the experiment with this other G here, accepted G, that's given in the books, 9.8. And I get just 2% of difference. Don't forget to put all the units here. You're going to write down the R square. You're going to write down the equation that you obtained here. Note, see that there is a small, there is a small intercept. Okay, even though we release the card from rest, because we're doing an actual experiment, it's never 100% what you'd expect for this for the intercept, right? And here's my R. My R is very, very close to 1 for math and line labels. Let's see. I want this guy with format and line label. Oh, right here. I'm going to put the numbers with more decimal places. I'm going to put the 6 decimal place. Let's see what we get. 999,877. Okay, so he just rounded it up to 9999. And you log number of data points here, R square here, and you find out the CL. That's what we have for this experiment. Any questions? I want to go one by one, see if you're doing something there, and okay. This slope is twice the acceleration. Acceleration, right? Calculate acceleration of the cart. Yeah, it's K, right? Use the acceleration of the cart to get the acceleration of gravity. And how we do that? Let me do the drawing here for you. You go. Here's the I'm gonna need here you go. Oh, I want to need this guy. Oh, here you go. Vertical direction. Okay. Vertical direction. Look what we have. We have this direction along the cart. We're gonna have a triangle, rectangle, and there's the vertical direction, right? When we put the cart put the track right under this inclination, what happens when we put we dilute the acceleration of gravity? That's the role that the inclination of that's the role that the inclination of the track, that's what the inclination of the track does. View, I want grid lines. Yeah, here you go. Grid lines, and I'm gonna line up with my grid. I'm gonna release. Okay, so here you go. You have this angle. That's G, right? So if you know this angle and this hypotenuse is going to be the acceleration of the cart. Okay. So G divided by that should be equal to this, to the sine of this angle. And the sine of this angle is going to be what? It's going to be 1 meter, right? And it's also related to the, here you go, it's going to be this triangle here, okay? This triangle here. The shim is raising the track and gives like a trigonometric relation for the acceleration. That's how we do that. Now let's see how you folks are doing and make sure you are working. We still have 20 minutes to go. Excel. So the first thing I'm gonna ask you is the graph. Hi, Sky, did you plot the graph already? Let's see if Sky is here. Yeah, Sky is still here. Hello, Sky.
Hello.
Did you plot the graph?
Yes.
Okay, graph is good. And Tessa, did you plot the graph?
Yeah.
Good. Destiny, did you plot
Yes.
it? Good. Next is Gael. Gael is not here, right? Nope. Ridwan, did you plot the graph? No, not yet. It's working. Okay, gonna put here working. Ashley is here. No, Ashley is not here. Norberto, did you plot the graph? Yes, good. And Annabelle, did you plot the graph?
Yes.
Good. And Vanessa, did you plot the graph?
Yeah, I did.
Okay. Next is going to be Catherine. Did you plot the graph, Catherine? Catherine isn't here. Oh my, she left us. What a shame. I'm going to put a half here for her. Okay, and Camden, did you plot the graph?
Yes, but I don't know what to write on the chart title.
Yeah, you gotta look at what did you put in the y-axis?
I didn't do. I only plotted the chart along with R value and the trend line.
I know, but what goes in the y-axis and what goes in the x-axis, right? Here you go. Here's my
The
chart,
V?
right?
Oh yeah.
Right? What does it go in the y-axis, right?
Right.
And what goes along the x-axis?
So do I just need to use like D and V square as
Yeah, and which one is d? Which one is v squared?
I think it's the V square is the Y and X is the D.
Yeah, that's right. And now you go ahead and you put the axis title, right? The title of the axis. Do you remember how to do that?
Yeah.
Okay. And don't forget to put the units there too, right?
Okay.
The units in the graph.
But I
Yeah.
have a question.
Yeah.
These Y and X values are written in scientific value. So I was wondering if we needed to make it to like number and stuff.
Well, there is a very good rule of thumb.
Uh-huh.
Anything that's greater than 10 to minus 3, you put as a number. Okay, let's use this rule of thumb. Okay, I'm going to type that out here for you. Okay, any number between, let's see, between minus 0.001, any, let's see, not any number, let's see, any measurement slash result between 0. Any numeric value of a measurement slash result, any numeric value of a measurement slash result between minus and plus, right? You format as a number. Okay.
Okay.
Make sense? Any other numeric value slash any numeric value of a measurement result outside this range. Okay, you format in scientific format. You use format number four. You use a number format. I'm just here writing it a better way. Any numeric or value of a measurement result outside the range, you use scientific you display, right? You display it in scientific format. You display it in a numeric format. Okay.
Okay, so and I have another question. For the axis options with bounds, right? Do I need to adjust the minimum value to like 2? But I don't get this. There's like 2E-01.
Are you talking about the graph?
Yeah, the graph.
Okay, you're talking about this empty space here.
Right. Yeah.
Okay. So
the Y value. You see, like there's like 2E-01. I don't know if I have to do that or not.
Okay, but I'm gonna do an example here. Here you go. I'm gonna 0.4. I'm gonna go from 0.4. Okay. All the way up. Let's see. Can I do that all the way up to Okay, don't forget those values here are, doesn't have enough single digit, doesn't have enough decimal places, right? And I'm going to format not in scientific, but in number. And I'm going to increase, let's say 2 decimal places, maybe. Yeah, 2 decimal places is good enough for me. Okay, where am I going to stop? Let's see, maybe we can stop at 1.6. Let's see if I can stop at 1.6. Okay, this one, and I want to see this one. What I'm gonna do here? Number, not scientific.
So switch it to
Okay,
number.
I'll go 2 decimal places. Here you go. Okay, so we're gonna go from 0.1. 0.1. Yeah. Yeah, I think I got it. Okay, I might want, let's see, I might want to go to 1.5 here. Maybe I'll go to 0.45 to look better. Let's see. Oh, I see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This one I'm going to give a little bit of room. Let's see, can I give a little bit of room here? Maybe. Let's see. Point, and then I change it to 0.1, 0.05. No, no, too close. Too close, too close, too close. Let's see what I can do. 1.65 is not a good one. But wait a minute, I can shrink. Let's see. Maybe 0.1. Yeah, it looks like I got it. See that? If you play a little bit with it, you get it. You come to the point that you get. Okay, so you cannot do better than that. Optimize as much as I could.
Professor, can you show me the axis value again?
Yeah,
The
here you go. Double click. What do you want me to do?
0.02.
What do you want me to do?
I just wanted to see what kind of value you have.
You want to see what?
The axis value, because mine is mine is not as same as yours.
Well, yeah, it really it's not the same. So you have to adapt to your data points. My data points is different. Is going to be different from anybody else here in the classroom. Okay.
Okay.
So you have to play with your own data points in there until you get a nice graph just like that you optimize as much as you can.
Okay.
Okay.
Thank you.
Okay, so let's see, and then we have someone else next in line. Victoria Preciado, did you plot your graph? Let's see, Victoria here. Oh, well, Victoria left too. Huh? I'm gonna put it left. So I'm gonna put 0.5 left. No? Next is Alexis. Are you there, Alexis? Yes, you plot the graph? I presume you did, right? Okay.
Yeah, I plotted it.
Okay, good. Marco Daniel Sanchez, you plot the graph? Okay, good. So what else do we have to do? What else do we have to do? Percentage difference. Okay. Right, you get the percentage difference by typing the slope there in the last table. Okay. And with the R, let's put one more thing here. Get the R square. Okay, you need the R square here. You need the slope. Okay, after the slope, you get the percentage difference. Okay, and then you're gonna need the CL. Oh, and don't forget, there's more, right? Don't forget about the units, the sig figs, right? So we have all that stuff. Log the R square in the table, right? Log the N in the table, and so on. Make sense? Any questions? We have 6 more minutes to go.
I have a question about the percent difference. I forgot how to get it. Do I need to that's where you use the CL minimum and maximum values, right?
Let me see. What do you want? Do you want the percentage difference or you want the
Yeah,
CL?
percentage difference. The on top of the the where you find table 2-5. That's where I'm looking at
Okay.
right now.
Okay. For the
Unit.
percentage difference, you have to log the slope here. Okay.
Mhm.
Get the slope from your graph and type it here in this cell. Once you type the slope here, you're gonna get the percentage difference. Okay, here you go. I'm erasing, right? You can see that 0, 0, right? 100%. Once I type the slope, I get the right percentage difference. Okay, you do
Okay,
that?
but which one do I need to type? The slope the 0.260, right?
Yeah, that's the slope, right? The slope of your regression curve.
Oh,
My
okay. Oh,
case-
now it changed.
In
Yeah,
my case is 0.26025. In your case, might be something different.
yeah. How about the units? What do I need to
Yeah, I
type?
want you to find that out, right? The
Mhm.
slope of the unit is going to be the slope of the vertical axis. No, the slope of the unit is going to be the unit of the vertical axis divided by the unit of the horizontal axis. You gotta do your math now, okay?
Okay.
What's the unit of the vertical axis?
So it's y over x.
Yeah, but you gotta get the unit of the y-axis. What's the unit of the y-axis?
Like total value.
What did you plot along the y-axis?
Mine is like the v square.
Oh yeah, the v square. What's the unit of v square?
Let me see. It's like 0.43-ish, I think.
No, I'm asking the unit. The unit.
Oh, the unit. Okay.
Yeah.
0.2603x plus.
No, that's not the unit. The unit is either gonna be meter, it's gonna be seconds, or it's gonna be a combination of that. That's what the unit of v square is gonna be. Okay, it's not a numeric value. It's going to be a. Right?
Right. That's a micrometer. Oh no, wait. Yeah, micro. Yeah, microsecond.
Well, first, before you're doing that, fill up all the units here. Okay.
Okay.
After you fill up those units, you have a better idea what's going to be the unit of the vertical axis. Okay. Let's do this way.
Okay.
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 And anybody else? 11:57, 3 minutes to go. And okay, now we're gonna go faster, right? Faster than the lab one. Remember, lab one, we spent how much time? We spent what, 3 or 4 or 5 meetings, right? Now, from now on, it's gonna go quicker, right? So here you go, lab one. We spent, we did this 1, 2, right? 3, 4 meetings for lab one. Oh, even more, 5 meetings, right? Okay, now we're gonna go quicker than that, right? We're gonna go quicker than that. So lab 2 now is due next week. Okay, so here you go. Report for lab 2. Report for lab 2 due next lab meeting, which is going to be October October 18, okay? Report for lab 2. That's what we're going to do. And report lab to do. Here you go. Report lab to do. Right? I'm not going to boldface it, but I'm going to leave it italics. And then we do lab 3 next time. Okay, we still. What are we going to do? We still have to. Yeah, we couldn't finish laws of motion, right? So we're still going to look at laws of motion next time. I'll have to keep on updating this. We're not going to be able to cover all those 5 chapters, right? I'll have to move work to the following week. Right, linear momentum. Here we go. As we go along, update the syllabus. Okay, and it's 12 noon right now. So we can stop and we'll meet again on Monday. Okay? So see you next Monday.
Professor, I have a question
Yeah.
about homework.
Uh-huh.
It's about vector.
Uh-huh.
Question 15, I think. The weather monitor.
Okay. Which homework? Number 1, 2, 3?
It's like 1-3 vector. Question 15.
Oh, it's homework 1? Is that what you said? Homework 1?
Homework, it's like third one. Yeah, yeah, that one.
Third homework. Okay.
Yeah, but
Chapter
it's like,
1.
yeah,
Homework
chapter
3,
1
chapter
vector.
1. Let's go here. Open assignment. Must be this one here.
I think it's question.
Oh, wait a minute. Let me close. Let me stop the recording here.
Okay.